versions, MX plus B for, a thermistor or something like that. The limits of that, it goes from here to here, and anything above that is in the red. An exchange protocol, so it can actually define state machines. You send this command, I expect some data back within 50 milliseconds, and it can define those kind of things. So it really is a specification that you can use for tooling to then auto-generate all kinds of artifacts. And the idea, so you take a star tractor and have an electronic data sheet for it, and now I can take that and auto-generate the interfaces that the ground might see for control and telemetry, the software that an Attitude Control System on a spacecraft would need to use, and not the algorithms, but what the interfaces look like. And software tooling, again, for, a crew on the surface of something, or, a rover, something like that. So they can take this information about this star tracker and then auto-generate a lot of artifacts from it. So same for, thrusters, actuators, and software, or even a processor. So these things can be combined in such a way as you deliver a processor with a lot of interfaces, and you bring all the data sheets together and perform the same kind of function, auto-generate the controls for it, the configuration for it, for the different types of systems. So it's widely applicable. The long-term vision is manufacturers actually provide these SEDs with these devices. That was the long-term goal. We worked with the Office of Director of National Intelligence on this a number of years ago, and they were really interested in this because it keeps the cost down and allows you to auto-generate a lot of things. So where SWAS standards might be used for, interoperable communication stacks. Again, they're not the stacks themselves, but the definitions of that. So the subnetwork would specify, wired exchange and discovery between internal systems within your rover or your lander. In dock systems, two systems meet. What does the data exchange on that look like at the subnetwork level? So it's applicable to a lot of things. The SWAS SEDS specifies, the interoperable data exchange between systems. So if you have a display system, which I have on the diagram up there, it's like, what's the format on the wire of the data that's coming in? What are the red limits and stuff such like that? So you can actually put it up on a screen so somebody can see it. The data sheets they describe whatever the protocol is. So you can auto-generate the software that creates the data fields and the display. Same for a crew. If you want to describe the health data, that's got to come from a crew member. You would use a data sheet, and then that can go to the system that's going to process that. And here's the format. Bit 5 means this. This 32-bit word means this. So it's very powerful in that way for auto-generating software in control systems. The third area or working group is, again, the wireless group for interoperable communications. Again, there are profiles of the existing terrestrial standards as being applied to lunar surface systems and crewed systems internally, with the spectrum prohibitions, as you heard earlier. So one of the things that's kind of different here is we really think this is going to have long-term positive impacts for device sparing, fault tolerance, and the ability to take, a component from one system, bring it over to another one, and potentially auto-generate stuff or have it accept those kind of specifications. So if you've seen The Martian, you see that they're able to take stuff from here and use it over here. That is really important for long-term sustainability on surface systems. You can save the day, so to speak. Sort of a more recent example of that was Intuitive Machines lander. They were able to take the sensor data from one system and use it for their landing. I mean, that's pretty powerful as far as, fault tolerance, being able to take and repurpose something you already have. And having definitions like these of what their interfaces are and what their limits are and their precision and stuff is really powerful to enable that kind of stuff. It could save, crew lives and such. So anyway, so I think I've got one more chart here to finish off. You see, I'm sort of passionate about what we do, like most of us in the standards organizations. So the SWAS standards are actually called out in NASA's Deep Space Interoperability Standards. There's several CCSDS standards that are called out in there, and SWOS has got a couple in there that are important. The dictionary of terms. So in the data sheets, you all call the same thing, and it means this very specifically. That's an important standard. And they're being used across the Artemis program. So it's in the Artemis standards to call out and to use these. So ESA is using it, and JAXA is using it, and CSA and NASA, of course. So CCSDS, I think I wanted to mention this. We welcome agency and industry, other agency and industry participation, to really make these standards, make sure we cover all the use cases that are applicable. So we're making something that you can actually use. That's really important.
Are there any questions for Jonathan? Onward interface. Yes, please.
Yeah, thank you very much. How you mentioned the dictionary of terms. How is that distributed, and do people access that?
So our dictionary is in SANA, and it's kind of incomplete. It just talks about the protocol stacks that we're trying to describe. So an attitude system would have to come up with their own DOT, right? And the power system would do theirs. And those are important. So we're not the domain experts there. So we would allow other people to do. And it actually is really important to agree on what does this mean. And we see that in a lot of standards that they're not specific. And that's not good enough. I want to be able to auto-generate software artifacts, test them, and terms matter. Words matter, as my wife always tells me.
Okay, thank you.
Any other questions?
I wonder if I might sort of augment that, because in CCSDS, we also have something called the Space Assigned Numbers Authority. It's an online set of registries that are used across all the working groups. And that actually has all the terms defined in all of the CCSDS standards. It's online, it's open access, searchable. And there are a number of other registries there that cover all the different protocols you've been hearing about.
Yeah, thank you for adding that.
Okay, I would like to emphasize this last statement. CCSDS welcomes agencies, but in particular also industry participation. This was the original idea why we wanted to have this forum here, in order to see in how far we already meet the expectations of industry, but we would also like to encourage industry to come up and work with us on the future standards. And I think after the lunch break, we are going to have a panel 3 session where we will see contributions from industry and academia and some agency presentations also on this topic, LunarNet interoperability, and how eventually the standardization activities that we try to do conduct in CCSDS might help to bring really this lunar economy about. And I think we are now going to have a lunch break. Let me want to say something how that works.
I have no idea how that works, the lunch break. But thank you for surviving the first half of the forum. And Diane, is there any tips?
Is like a cafeteria thing. It's called ice theory, but immediately to the left of it, there's kind of a health food vending machine, if that's to your liking. So you want the star, but
Is that possible?
there is coffee down there.
The green badges.
If your badge says if you need one, just it'll say on your badge. No, you need somebody who actually works.
So if you have a green badge, you do not need an escort, but you cannot escort a foreign national. If you're a foreign national, find Diane or one of them. Right, delegate here. Okay, please try to come back around 12:30, give or take, especially the speakers. Can I ask you to stay at the table so we can take a group picture of the area directors?
Standing or sitting? Do we come from the front? Okay. Pretty official.
Oh, yeah. Oh, that's great. They are.
Yes. Okay. Yeah. It is. You just go down the steps all the way down. And right to the base. Oh, thanks. We are. Oh, okay, thank you.
Come over here. And Jenny's starting to get back. It's always once every 5 days. So I remember I'm so proud of you guys.
Do you have a travel office headquarters? Or do you don't hotel flights yourself, or do you have a?
Hopefully it was right. No, We have a place called travel fairs. We're supposed to go through them, but because I'm a travel fair everywhere and I'm proposed, I do it myself and I leave it at the point where she has. When they do it, and the rest. They tell me to do that anymore, but
So you're going to concur and work it yourself?
I leave it at the point says, there's something like laws or something meaning not move forward. I'm there, you know. Because why? Because I hate having to fill forms with time, so somebody else can make a selection for you. And you can just-
Well, that's not the problem. Our travel office requires director approval. Like either center director or division director approval if the booking is within 90 days, 90 working days of travel.
Well, I gave mine ahead of time and she sat on it, so I'm following the instructions from the center, which is like 2 or 3 travel preparers per division. So if they tell me something, I'm gonna be like, we're 100 and it should literally start for 100.
It is.
Yeah, so travel's not exactly.
And they sit on it for like 3-4 months. And then when they go to book and they're like, yeah, the hotel you want is no longer per diem. No joke. That's fine.
Are you watching?
Do they know they're right?
I have nothing to say. I said anything, so.
I tell you, it's not pleasant to travel. But they don't let them. Send it on.
Expensive enough.
All of the people that were the agents from NASA, Sammy. Since Jovin is coming, he's also a director. Then Peter, me, and then the Johnson guy is calling in because he didn't come at all this week, I think. And then whoever we have for the area. And Sammy. Not the editor. Yeah, I remember I talked to you about the names. I will find out. And he's making stuff.
You ever figure out who's overseeing?
Yeah, so. The contract, well.
Who's overseeing?
Okay, so because it's divided, he is under the government.
Yes.
And then the other one was the one that I had to figure out, which is that. So fine, and I got the first report from them. That's the one I had to figure out because it's really Jim Armitage, the task leader now, so he was receiving it when I. Although back to the.
So you're back to blue minutes.
Starting to be, let's say. Did you eat?
Yeah, I brought it back.
Me neither. Do you want some chips or what? Very simple de poner. No, that was my plan B, okay? Oh, wow. So mine went, I mean, was my honest mistake because I did. I probably looked that I didn't put the right last names. So I used two last names. So that was mine. I admit, my bad. Now that I read the link, it will say in gray. We had the other swipe of that. Exactly.
So tomorrow, we can try spreadsheet. Start next year's function.
I had to get my notes. I sent an email with preparation. So one was some questions in general for how we're gonna message the next agenda. Because I need to prepare something eventually to educate you. And then the other one is here. So that we can, you see, I call it. I need a quicker way to be like, this area, or this work, this area, that's what we're working on. For now. And where is that leaking? That's what he wants to see.
That part of your conversation showed it.
Yes, yes. Yes, exactly. So so that's the part, because we can say a lot of stuff. Like I need to be sure why do we care or they care. So that's the kind of.
People are just.
Then they don't care.
Yeah.
I mean, even if we're gonna restructure, let's say we find some things that are, we need the money. This is not a scenario where like, oh, here, I can give you $1 million back. It doesn't, it's not like, I already know. Maybe in this case, it's pretty like another 100% from center. You know what I mean? It's not a case where I'm giving money back. And then I'm also trying to show to another day. There's this IOAG stuff. They need to start. I have that. It's a class. All of it.
It's like European. Where it's at.
I know, it's just, you know, they like a way of communicating. And there wasn't a conduit for a while. And honestly, when you were there, and me here, now we're all kind of a little bit overworked. It's supposed to be, right? So it takes some time to send message to a manager that has never signed the CCSDS to. This guy over there, his head has the cap.
Data centers. Good.
Yeah.
And I think.
That's so cool. Yep. Hey, thank you. Exactly, that's exactly like a photo. There's gonna be a. We can call it it's but not standards, otherwise. I did take it, but what do it with me? Thank you. I did it with just the stuff.
This is a video now, which you know, channel.
But imagine the warehouse. This is my plan because I didn't order food on time. There's plenty of food. I guess they don't like it that much.
Yes. Oh, yeah. Steve down.
Right. So he and I partnered. So I have central social service part.
Okay.
So it brought me back a little bit. Another guy. They wanted to have the four people with me.
Studying for a while.
I worked it out.
Okay, so we can talk to you on chat.
It's coming tomorrow. Well, are you?
I don't know, that's what we're working.
Okay. I invited him for tomorrow.
There you go.
If somebody can, that's what I mean.
Sounds like get a job. Issue
I'm hoping to find some help. I don't know. It's fine if it's replaced. Makes sense. Well, in a perfect world, it makes sense. But my managerial has to be because training will be always. Yeah. Oh, well, yeah, that's stated that way. There's any event that has good passion. Nice. I didn't want to start with girls. I'm tired and I don't. No, it was hard for me and I was doing the same. I woke up. That's why I keep knowing in terms of your senior or home and drive. But anyway, I said after 7 days, in the morning I packed like to my friend's house. I drive and brought her to the there. And then I can take her. I told everybody, I said, 9 or 9:30. I don't know. You never gave that up? Okay. Okay, then that's fine. What happens when we get there? Well, I ate at home. I don't want to eat much, but I ate. Yeah. So I did a little bit of that this time. And now, hopefully, now what's even that sort of I wrote all their What's I've been writing them down. Just to see what's to do I had a full week of fun in this class.
It was,
It was closed at school. I was starting because I didn't have my snack. I don't want to read that. Also, cooking up a household. Are we back? Don't worry. I don't know. Ask him.
For tomorrow, what kind of stuff are you looking for? Why can we consider?
I sent an email. I looked up for me. That was last week. So that's kind of like a whole follow up. Yeah, like what we're working on. What how are we trying that stuff? Like the demos. Yeah. So, like, I don't know if we're gonna do it for one area or all of them. I think so. Yeah.
Mine's on call. Very sure. But it goes back to what you were saying. It's only.
Okay.
Yeah, well, I'll talk about all that. They all interact.
Yeah, it was him who brought it up in a way. So they gave us access to their account thingy to look for some stuff. So I'm gonna look for some stuff, especially on some notes like this to see. If I see something to share, I will. So they gave us, everybody can, they gave us that we can request access to their notebook. Yes. Yes, they were happy about that. So for now, I have some notes I haven't sent because I haven't finished this yet. But for now, I'm going to go through whatever the one where the chief engineer guy is going to see how it passed. And then I told her about our interest, some maybe just for the title. Yeah, that's kind of where we are. And then she told us to look into the document and see if it's something. So I was gonna look into that and then maybe send some stuff around. They have optical intersatellite telescope. I have no idea. I have to look for the company. Okay. Oh, the battle.
Not sure if the logistics will work out.
Oh, no, no. I didn't donate any resources. I will get back. I mean, I don't know all of these deals. I don't know. I was just gonna bring back to him and come down to the guys or whatever. I'm just a communicator. Okay. Yes. I don't know, but that's what I was saying. That NASA is still over the thing. But I think not they added the NASA stuff to everything from that economics standpoint. Yeah. I think it started like a mechanical thing, which is why we did you mentioned here, like more like a payload kind of something, I don't know. And then it evolved into data standards, and then I never went to scan. I think that's what happened. But one of them good well, program was one guy who's going to the meetings and being lost. He's like, I really don't know what they're talking about. It's because we did a standard. That's what I think it's because it started non-data standards. It started kind of chief engineering stuff, and then somehow it evolved and was lost, and he never called anybody. Yeah, things to fix. I love my job. Every day. Yes, yes. Yes. That, yeah. Yeah. Peter did ask the question about its prototypes and stuff, and she said they were tracking where funding was needed from the agencies. You know, so at least they acknowledge some prototypes needed for interoperability and all that stuff. But yeah. Okay. Yeah, we're still on time for some of them. Yeah. We can all move to space. They're like, oh, we'll make our own. Oh, okay.
Can you please start taking your seats? Can everybody please start taking your seats? And if we can have the speakers in the next panel prepare themselves. There is no room at the table at the front for all the speakers. You're welcome to sit there, some of you, or stay where you are. It is up to you. Yes, you're welcome to sit here, but there's not enough for everybody. If you want to make a good picture, go for it. Yes. Yeah, you'll be introduced by the chair. You can.
You're not going to sit up there. They're going to run my slides?
Yes,
How do I click them?
there's the clicker. Forward, straightforward, yeah. So again, for the speakers of panel 3, we have, I think, 9 speakers, so there's not enough room. Some of you are welcome to sit here, make a good picture, but otherwise the chair will call you from my paparazzi here.
Well, since you said I could.
Yes, you could go for it. And speakers, there's a clicker here. Amber will set things up and then you can move the slides from here. Please wait for the chair to introduce you. And because this session is a little crowded, it's 10 minutes per talk, give or take. If it goes a little over with some good questions, that's okay too. So we'll just wait, maybe. Are all the speakers in the room? If you're not in the room, raise your hand.
If you'll find out. Where's the chair? Ah.
Okay, thank you very much. Let's start the panel 3, Industry and Academia. So I'm chairing this panel. I'm Masaya from Japanese Space Agency, JAXA. Okay, so there are 9 panelists. I'd like to start by Thomas Marshall Elbachs from Space Initiative Incorporation. The title of the presentation is New Lunar Position, Navigation, and Timing Reference System. Okay, please start your presentation.
Ready? Good morning, everyone. Or good afternoon, everyone. Sorry. So I'm going to talk a little bit about history and a little bit about physics, and not so much about protocols. So, you know, people use these terms all the time. It's useful to give a few definitions. A reference system is a way, you think about it, the way I think about it is it's procedures and protocols and mathematics and so on, typically embedded in some computer system or systems to relate certain kinds of observations to things you want to know, like where you are. So in the period starting about 1970 and I think kind of ending in 2000, all that really is going on today, we set up a reference system for the Earth. It has a bunch of pieces. It has a terrestrial piece, it has a celestial piece, it has propagation equations between the two things. I wrote one of them, or organized one of them. And it's how if you use GPS at all, you use it. You don't know that maybe, but you use it. And so then reference systems frequently have reference frames. Now, sometimes these might be ephemeral, but a lot of times they're not. In particular, there are 2 big ones here, the ITRF, International Terrestrial Reference Frame, which is a set of positions and velocities, because even back in the 80s, we realized we can't ignore continental drift. So you have to have that. 5 centimeters a year is huge. I mean, that's what Hawaii does, for example. And then there's the ICRF, the International Celestial Reference Frame, which I also helped to set up. And that's extragalactic source positions. And that is actually the inertial frame that all of this other stuff is tied to, okay? So if you use GPS to find your hotel tonight, that's depending on observations by VLBI of quasars. Now, it's not the only thing it's depending on by good measure, but it is depending on that. And those are not observations in the far past. Those are continuing observations that are going on today, even as we speak maybe, but certainly today. And all spacecraft navigation depends on this. And I said, most terrestrial navigation, if you got to use a sextant, well, you know, you're not, but not many people use sextants nowadays. So my opinion, and I was grandiose here, the development of a cislunar civilization, because it's commercial, scientific, governmental, so on and so forth, we're all together in a sense, you know, it's all the same biology, is going to depend on pushing this infrastructure out to the moon. We know how to do this. You know, we've done it for the Earth. And a reasonable goal, in my opinion, is, and this is more than most people are thinking of, I think, but is centimeter absolute positioning, basically everywhere in cislunar space, at first on the near side, for obvious reasons, and then later on the far side. We have the technology to do this. We have the knowledge to do this. It's a matter of pushing it through. Okay, and that's going to require both a reference system, but in a sense we have at least the sort of, you might say, the mathematical part of the reference system now. Everybody thinks that general relativity is expressed in a parameterized post-Newtonian approximation is good enough for solar system needs. Yes, you need to specify a gauge, but we've all settled on a gauge, and don't mix gauges. And you know, so we think, and this has all been tested a lot. So we think that the reference system is fairly robust. Now there needs to be pieces in that reference system that aren't there, but but we think we know how to do that. It's the reference frame, you might say, and the relationship between reference frames, that's the pieces I was talking about, that need work. So the lunar reference system, in my opinion, is going to be based on the lunar surface eventually. And the reason for that is twofold. One is the lunar surface is going to be where people are, and machinery is, but also is that's the stablest
Actually, that is the stablest place in the near Earth system, period. The moon is an older body, it's a smaller body rather, it's old, it's not dynamically dead, not for that, but it is a lot quieter than the Earth. What happens in a few days on the Earth might take you a year on the moon. It is not dynamically dead, and it's worthwhile going into a little bit why it's not, what it is. And there's a lot of that's because it's next door to the Earth. But the moon is gaining orbital angular momentum from the Earth's rotation. The Earth's rotation is slowing down. The moon is receding at 38 millimeters a year, which doesn't sound like a lot. That's a semi-major axis change, but that's 4 meters per year squared in longitude. So that's a pretty big effect. And I have reason to believe that there's actually variations in that it's not just a constant change. It's because it's based on ocean tides. Oceans change. We have global warming going on. We go to climate change. We have, sea levels are rising and falling, and so on and so forth. Oceans are going to be changing. You have El Nino events, et cetera. That's going to change. We have lunar librations, which are the equivalent of the Earth rotation modes, where there's a polar motion, there's a free libration in longitude. The moon can rock back and forth. That's about 10 meters. We really don't know at all where that came from. Yes, there are theories, but there's no consensus as to what's driving that. And there is an LLR estimate of a long decay time. It's not even really clear to me that that's that reliable, and we could get into that. But just, all of this needs to be buttoned down. If we're trying to do really sub-meter positioning from the moon, we need to button all this stuff down at the sub-meter level. I mean, that's just sort of obvious. There's a little bit of other stuff there too. NASA has taken the lead of this on the Earth. NASA had the Space Geodetic Program, SGP, project, rather, not program. And that really set the groundwork for the system we use on the Earth, where we nail all this stuff down. We know what causes Earth rotation. We can monitor it. We know what causes polar motion. We can monitor that. Earth rotation changes. We can monitor polar motion, so on and so forth. Okay. And my position my feeling is that to do this at the accuracy level we need, we have to not just rely on lunar laser ranging. We're going to need VLBI or an analogous service to provide transverse position. It's a simple geometric dilution of precision thing. If all you have is radial position determinations, which is what we rely on right now, then how do you separate the radial position of the lunar orbit from the radial offset of the station in the center of the moon? That's very hard to do. And the evidence for that is in 50 years of lunar laser ranging, we've determined, a lot of which has been supposedly at the millimeter level, and at least, in our RMS sense at the centimeter level, we still haven't determined the lunar semi-major axis to better than about 20 centimeters. Whereas if you and VLBI has the same problem in distance. VLBI determines transverse positions, LLR determines distance. You could put the two together and you have a nice 3D determination of position. I can actually show you a slide on that. If you look at the bottom, this is for Malaport Mountain. We did this sort of stuff for a bunch of places that people are talking about going on the moon. You have the two together and you observe for a month, and this has the usual restrictions on elevation angles and so on. Although I am assuming that Malaport Mountain, you can see the Earth the whole time, because I think you can. You can do 3.5 centimeters in lunar semi-major axis in 3.5 millimeters in lunar semi-major axis in 1 month. That is 1/10 of the orbital motion in a year. So if you could do this, you can actually track this on a monthly basis. You could track that orbital precession on a monthly basis. Now, it's mostly actually you're tracking the longitude change, but Kepler's law says it's the same. There's the LLR data. Over time, you can see it's gotten better. It's never gotten much better than a centimeter, though. It's not quite, it should be better than that. It's not quite clear what the systematic error is there. So that's something that needs to be looked at. Here's a generic VLBI picture. And then I'm going to close. And this is the problem here. This is exactly the problem. This is at Rena Gamma, which is a CLIPS landing site. This is what the moon does, the Earth rather, does in 1 month. Unlike satellites on Earth, which rise and set, or the moon on Earth, which rises and set, or Mars or whatever, on the moon, the Earth just does this little noding around up in the one part of the sky, and you just can't get a good separation of, it's a dilution of precision problem. It's a correlation problem. You got like 9-9 type, 5-9 types correlations. So I want to talk just a minute about lunar relativistic time. Now, this is something that we know how to calculate, or at least think we know how to calculate. And, you know, the equations are fairly straightforward. You need to worry about the kinetic and the gravitational redshift. And this is the lunar relativistic time between the surface of the Earth and the surface of the moon. So you have a clock, TAI, and what you might think of as lunar proper time. So if you have, just take a clock from the Earth, stick it on the moon, it should be, this is the relative time difference. You will notice that there's about, if you translate this into microseconds a day, it's 56 microseconds per day. I might point out that the Earth's, the lunar surface redshift is about 2 microarcseconds a day, and that's why that number, they dropped that from the certain press release that came out April 4th. And there's about a 200 nanosecond equivalent nodding that's in the monthly going back and forth. My feeling is we should just absorb that redshift, or actually blue shift. We should redshift the lunar clocks so they match terrestrial clocks, just as we redshift GPS clocks so they match terrestrial clocks. So we don't have to worry about leap seconds on the moon. Be simple about it. We can do that. We can't really do that from Mars, but we could do that from the moon. So that's it. Thank you very much.
Thank you very much. Is there a question or comment from the floor? Okay.
I don't have the microphone.
Okay. No, thanks very much. I resonate with everything you say.
Thank you.
Actually, we are proposing that. So we are proposing a GPS-like system already this decade on the Earth, on the Moon system, and we are proposing a local differential station on the Moon surface, combining 4 geodetic techniques: BLBI, laser retroreflector, direct to Earth ranging, and then the GNSS. So to achieve our estimations is centimeter level. We are proposing that there is an atomic clock there, and our estimation gives us that
we're
even
clearly
with,
thinking alike here, because I would propose all of those things.
okay,
I actually had a slide on atomic clocks. And I
okay,
took it out.
this is what we call Novamoon. This is going to fly in Argonaut 1, and then in addition, we want that to provide local differential to the GPS-like system, and then our estimation gives us sub-meter accuracy today in real time. Is we have the surveying with centimeter, and obviously the question is,
Well, yes, and then we'll find out, right? I think we have work to do there, and I think there's an intersection of science and engineering. There's engineering stuff you have to do, but it'll have good science. It'll lead to good science as well. So you have time enough for another question, or is that it?
It's time, so
All right.
we need to move on to the next paper. Thanks so much. Okay, the next speaker is Alberto Montira from Spatium Corporation. The title of the presentation is Building DTN Capabilities in Lunar Service Provider Networks. Please.
Thank you, and good afternoon. I am co-founder and CEO of Spatium Corporation. We're a startup aiming to contribute to the creation of the interplanetary internet. We're also CCSDS associate members through NASA. And today, I'm going to talk about something that is very important and something that came up during the CCSDS session, which is how we build DTN capabilities in LunaNet service providers. LunaNet service providers, I'm going to be using the term LNSP. That means LunaNet as service providers. Let me talk a little bit about the Spatium DTN platform. Our platform aims to operationalize DTN networks for LunaNet with network overlays that are open, that are multi-administration. What that means is networks that has participations of space agencies, private sector, and other organizations, and heterogeneous, which networks that are supporting different implementations of the standard bundle protocol stack. Our platform can integrate with mission and cross-support operations via APIs as well. The platform is formed by 3 major components. The first one is the Spatium DTN Manager. It is the manager of the network. It manages the network, the nodes, and its configuration and monitoring. We'll see some of the use cases in a second. The DTN managed instances are the DTN nodes, the nodes that contain the bundled protocol stacks and are deployed in ground, in space, into lunar, the lunar surface as well. And those nodes are managed and connected to the Spatium DTN manager through a management interface. And then the DTN CLI. It is an application that performs remote asynchronous management over the DTN network. And is the reason it is part of the product portfolio is because first, it's a demonstration of having an application that runs through the DTN. And second, because it is necessary. The same way any router in the world has a CLI, the same way you will need to have the same level of low-level operation capabilities in the DTN nodes. So let's make it real. Let's talk about an example, a scenario, and how we enable the DTN capabilities in the LNSPs. We're going to look at an example of LNSP1, which is the one highlighted in green, that deliver services through 3 major nodes: a node that is on the lunar lander, a node that is on the satellite relay, and a node that is in ground. With that network, the service provider LNSP1 is able to offer services to users both in the lunar surface, cislunar space, and ground, and is also able to augment their services by connecting their network to the LNSP3 in yellow relay services on the moon. In addition to that, this network can be used by other LNSPs, in this case LNSP2, that have a network with their LTV on the lunar surface connecting to the LNSP1. So let's look at some of the details and what are the capabilities required. First, the first key capability is network management. Being able to add nodes, remove nodes, relationships, etc. Second is defining a secure user to LNSP interface. That's critical to any service because you have to provide an SLA to the user, but at the same time, you need to be able to do that while protecting your network and protecting the other users that are using your network. Third, managing the inter-LNSP interface. As the example showcases, and this example can happen for real as soon as 2026. So this is not an example we're talking about here that it would happen in 2030, 2045. This is going to happen within the next 5 years. So the relationship between LNSP is going to be a critical one, and part of the LNSP is managing that inter-LNSP interface, set of interfaces. And fourth, securing user applications. The internet, our experience with internet has demonstrated that securing the main internet working layer, in this case, the bundled protocol, is necessary, but not sufficient to ensure security end to end. And last, enabled operations, whether we're talking about network operations, mission and cross support operations, how they benefit from the automation provided in DTN and the LNSPs. So let's look at the first consideration, network management. Network management is essential for operationalizing network security, for operationalizing SLAs, and operationalizing the proper operation and the services that offers to the users. It includes network configuration, includes management of contact plan, includes management of the nodes, among many other things. We have been working at Spatium to have a DTN manager that provides a user interface to perform configuration and monitoring capabilities. Through the interface, you can configure the network elements, you can configure the nodes, you can define things like node IDs, convergence layers. You can see the status of configuration, the status of the nodes, and even the status of the application. In addition to that, the manager offers APIs that we believe are essential to efficient operation. So first of all, to integrate with your own network operation services. Something to keep in mind is, as we talk about LNSPs, we're talking about operations that are specific, not specific necessarily to the mission, that are specific to the network, because that network needs to be up and running to deliver the SLA that you have committed to. You can also see something, probably not, it's not, cannot be seen really clearly, but you see that there are nodes on that network that are managed by other organizations. One of the things that are critical is that you need to have visibility of those of the network configuration elements, although you might not be managing those nodes specifically because they might be managed by another service provider. The second element is to deliver a secure user to LNSP interface. And for this, we established the concept of a DTN gateway, and we propose the use of bundle encapsulation. This allows to enforce user policies for security, forwarding, quality of service at the gateway, at the entry point. You can also benefit from performing topology hiding so that users only use default routes, similar situation as the internet today. And you can isolate the LNSP specific context internal to the network and those contexts that are offered to the user. Managing inter-LNSP interfaces. It requires, it's a start, and it's something that we discussed today during the CCSDS section or panel. It starts with a registry and with sharing interface configuration data, which is a topic we also discussed last week in the DTN working group, as the means to start the process to perform management automation, to ease the process of, for example, scheduling contacts, easing the process of distributing configuration and distributing the necessary policies, for example, BPSec related policies. Let's look at this through an example. It's something that we talk about very frequently, contact plan management. The Spatium DTN platform offers contact plan management. It provides a graphical user interface to create, activate, deactivate, and delete contacts. And then the manager is integrated with the managed instances through the Spatium DTN management agent to exchange the contact management controls and reports through the API, through the network, sorry. In addition, the manager offers an API so that it can integrate these functions with network operations and eventually with cross-support operations as well. So that's a way to accelerate or speed up the process to set up contacts. You may wonder how real this is, and the reality is that this is very real. We're going to be demonstrating the Spatium DTN platform and its capabilities in the International Space Station later this year. We're going to be setting up a network overlay to demonstrate the core capabilities of a DTN network, setting up the overlays, exchanging or transferring telemetry and command data, setting up nodes as gateways, and application of a different set of policies. We will be sharing the results with the community, and I'm happy to discuss the details with you in another occasion. With this, I arrive at the end of the presentation. I will be available for the rest of the day for any questions or inquiries. Please remember the 5 key elements of enabling the DTN capabilities in LNSP: network management, secure the user to LNSP interface, in managing the inter-LNSP interface, secure user applications, and therefore enable operations. Thank you.
Okay, is there any question, comment from the floor? No questions? Okay, then let's move on. Thank you very much for the presentation, and let's move on to the next speaker. Okay, next presentation is from Rami Kozman from Satellite Technology Ltd. The title of the presentation is Interoperability Constellation for SSTL's Lunar Pathfinder. Okay, please start.
So thank you, Mr. Speaker, for the kind introduction, and thank you very much for the invitation to speak here at this forum. It's a great pleasure and privilege to be here. So I'll be very brief overview. Why do we want to put data relay satellites around the moon? Well, we all know that there's an emergent lunar economy. It's set to generate $100 billion US in the next few years, according to PricewaterhouseCoopers. Overall, government investments in this region are being higher than ever before in the last few years, and they will be reaching 31 billion by 2031. So what this means is over the next 2 decades, we'll see a number of lunar missions launching, and this will lead to a steady presence on the moon, which is great, but it has some challenges. And some of these challenges can be alleviated by putting a data relay satellite around the moon. So a key one is that when you have all of these missions on the moon operating, they're going to want to send their data down to Earth. And if there is no data relay satellite, they'll be trying to speak to Earth, and the ground segment on Earth will be very quickly oversubscribed. We're already seeing this now on the Deep Space Network, and it's likely to happen on lunar Category A missions as well. A second issue relates to line of sight. In such a historic building, maybe it's worth remembering the Apollo 8 mission and the astronauts who went around the far side of the moon. And we probably remember the audio or the transcripts from that mission, where there was silence as the operators waited nervously to hear from their compatriots. Now we have a similar issue with lunar missions here. If you have missions that are landing on the far side of the moon, they need a data relay to be able to speak with Earth. The third rationale for a data relay satellite relates to size, weight, and power. If a lunar mission already launches knowing they're going to use a relay satellite, this means they can use lighter RF hardware, less powerful, less performant hardware, because they don't need to speak 300, 400,000 kilometers. They can make do with 8, 10, 12, or 1,000 kilometers. And they can save that swap, and they can allocate it their primary payload, giving more science for your buck. So this is Lunar Pathfinder. Lunar Pathfinder is SSTL's data relay satellite. It operates in X-band on the downlink at a rate of about 5 megabits per second. And it can serve 2 users simultaneously in S-band at a rate of about 2.7 megabits per second. We're also flying a number of hosted payloads. Dr. Ventura-Treviset mentioned this in his presentation. So we have a laser retroreflector provided by NASA. We also have a GNSS weak signal detector, and we have a radiation monitor as well. A note on the commercial model. So SSTL own and operate the commercial lunar relay service, which is realized through Lunar Pathfinder. ESA are our key anchor customer, and they've purchased services from SSTL, which will be used in the future to support their missions. ESA have agreed with NASA to give a tranche of their services to NASA in exchange for a CLIPS launch, and ESA very kindly providing that CLIPS launch to SSTL to launch Lunar Pathfinder. And once Lunar Pathfinder is launched, we'll be able to service commercial users, but also ESA missions and NASA missions as well. It's important to note that Lunar Pathfinder is the first node in ESA's Moonlight program, and the services will be building on Lunar Pathfinder's capabilities, providing enhanced data rates, throughput, and additional bands. And Moonlight will be interoperable with international initiatives such as NASA's LunarNet and JAXA's LNSS. And the infrastructure initiatives will enable far more ambitious astronomy missions to the lunar far side through enhanced communications and precise PNT solutions. And SSTL are excited to be part of this moving forward, working with ESA and industrial partners such as Telespazio. So let's talk a little bit about interoperability. So when we first started doing the Lunar Pathfinder design, we actually were flying a UHF antenna. Our market analysis showed that there would be some lunar missions operating in UHF, and there wouldn't be any radio astronomy missions, so there would be a market to service there. However, as the years have gone by, we've realized that that's not the case, and there is going to be a radio astronomy mission going to the far side of the moon straight away. In fact, we're launching with one Lucy night. And so what we did was we swapped out our UHF antenna with a second S-band horn. This means that Lunar Pathfinder has no in-band emissions below 2 gigahertz, and thus we're respecting the shielded zone of the moon. Further to that, we've enacted some requirements to limit power flux densities of spurious emissions in various bands of interest. And we flowed down those requirements to our designers and suppliers of radio transmitters and filters, and we're making sure that we verify those requirements at equipment level and also spacecraft level. We also conform with a number of SFCG recommendations and ITU radio regulations. So these are 2 recommendations we conform with. The second one there, 32R5, has already been mentioned previously today. It outlines a number of different frequency bands that should be used in the cislunar region, and we're doing that on Lunar Pathfinder. It's worth noting that the first one there, recommendation 51R6, requests that people do not use more than 10 megahertz for their trunk link back to Earth. In fact, there's an additional recommendation 41-1, which was provisionally released in July 22 and then fully released in June 23, which is more stringent and says that X-band links should not exceed 6 megahertz. Now, that recommendation was released far after Lunar Pathfinder design was complete, and our understanding and hope is that that recommendation doesn't apply retroactively. So we've also participated with the review of the SFCG provisional recommendation 42-1 in August 23, and we've aligned our S-band frequency plan accordingly. So this is our understanding of the single access forward bands that will be applied around the moon. And in red, there are the bands that SSTL have filed in the Lunar Pathfinder API. So we filed for 2 of the bands, and we've also filed for an additional 4 megahertz, which is adjacent to the top band, which we understand to be available to do so in via the standard frequency filing procedures. Now, it's maybe just worth noting again that there's a slight discrepancy between what's on this slide and in this draft we've seen in August 23 and what's on the SFCG website currently. There's an October 23 draft which doesn't have the same frequencies, but I understand that's an administrative issue which will be dealt with and addressed in the upcoming release of the recommendation 42-1. Again, based on the same recommendation, we have a number of channels which we're planning to use. So this table here may be a bit difficult for the room to read, but on the left-hand side is the SFCG recommendation for breaking up the 2 5 megahertz single access bands. They've broken up the 5 megahertz bands into 5 times 1 megahertz chunk. And one of the 1 megahertz channels is used for hailing, and the remaining 4 is used for data services. Now, SSTL's Lunar Pathfinder requires 4 megahertz occupation to operate at a symbol rate of about 4 megabaud in GMSK. And for this reason, we are going to need to occupy 4 channels if we're going to hit our highest symbol rates. What this means is that there's a slight divergence from the channelization plan on the left-hand side to the channelization Lunar Pathfinder's plan on the right-hand side, but only in terms of the center frequencies. So users who want to operate at the highest symbol rate will likely need to sit at the middle of channels 2 and 3, for example, or channels 6 and 7 in order to hit those 4 megabaud. But apart from that, we think there's excellent synergy between our channelization plan and the SFCG channelization. The key area in which we're aiming for interoperability relates to proximity 1, where we've modified physical layer, coding, synchronization sublayer, and data link layer implementation. So our initial design in 2019 had assumed that the legacy UHF proximity 1 requirements were also applicable to S-band. But what we've seen over the years is that what works for Mars, UHF around Mars, doesn't really work for S-band around the moon. And we've had a number of different interactions with key institutional stakeholders and other LunarNet colleagues, which have led to several modifications being applied in proximity 1. So the first one is the S-band modulation scheme. The legacy standards request that you use split level only. And whilst that's a great modulation scheme, very power efficient, it's terrible for spectral occupancy. And so what we're doing is we're making sure that split level is used only for low rate comms, and we'll be using GMSK with baseband filtering for medium and high rate comms. The legacy coding was uncoded, convolutional, and LDPC rate 1/2. What Lunar Pathfinder is doing is we've added an additional LDPC rate of LDPC 2/3, which means you get higher data throughput for a given symbol rate or lower spectral occupancy for a given data rate. We were using variable length SPDU type 1, but obviously now we're changing things. It doesn't make sense to say it's type 1 anymore. So with discussions with ESA, it was agreed that we should be using type 4. And I understand that that's been discussed in the last quarterly meeting here in the last few days. Furthermore, we're also using version 3 transfer frames, which are specific to proximity 1. But we see with the release of the LunarNet spec that people are going to try to be using USLP and so on. So we are going to be using version 4. It's important to note that we're not using USLP. We're still using proximity 1 data link layer, but we'll be going, this will give us an easier upgrade route if desired. And the final modification we've done is related to hailing. The initial hailing was uncoded at a rate of 8 kilosymbols per second. But again, through discussions with NASA and ESA colleagues, we realized that this will be a bit of a problem for assets with low G over T. So we're implementing an additional hailing option, which is LWPC rate 1/2 coded with a much slower symbol rate. So in conclusion, Lunar Pathfinder will be launching in 2025. It's the first node in Europe's Moonlight system. We aim to be as interoperable as possible, and this will be realized through collaborative interactions with industry and institutional stakeholders. So thank you very much. Happy to take any questions.
Thank you very much. Are there comments from the floor? Question from the floor? No question, comments? Okay.
Gary Barnhart with XISP Inc. Are you envisioning that the lunar orbiters would be able to interact with other commercial spacecraft that will be in lunar orbit?
Yeah, yes, indeed. I mean, so we're already planning that Lunar Pathfinder will be able to operate with a radio transceiver, which will be on Lucy Night. Lucy Night is a radio astronomy mission that launched at the far side of the moon. The transceiver there is being built by a company called Vulcan Wireless, and we're working very closely with those guys to ensure interoperability. So I think it was mentioned in the presentation earlier that this is initial implementation of S-band proximity 1 services. So we will be able to work with those people. We also have a full ICD where anyone who wants to use Lunar Pathfinder will be able to use us. And we can also look in the future to be modifying Lunar Pathfinder, if appropriate, to be even more interoperable with the LNS-IS standards as well.
Great, thank you.
Thank you. Indeed. Yeah, thank you very much. Yeah, when I say NASA, I also mean JPL as well. They've been instrumental in helping guide the implementation we're using on proximity on Lunar Pathfinder.
Okay, thank you very much.
Thank you.
Thank you very much. Okay, the next presentation is from Massimo Capozzi from Telespazio. The title of the presentation is Moonlight LCNS European Industries Roadmap for Communication and Navigation Services. Okay, please.
Thank you so much. Good afternoon, everybody. It's a real pleasure for me to be here, to be invited in this very important forum. So today, I will very quickly describe the LCNS Moonlight initiative, and inside that the industry's roadmap concerning these very important long-term objectives of the European Space Agency. So as Javier from ESA told us in the previous panels, so there's two major objectives behind the Moonlight program. So the first one is the short one is to deliver an interoperable communication and navigation services in the cislunar region, and this will support the next missions from institutions and from commercial entities. So the short-term objectives is to for the industry point of view. So from Telespazio as prime of this industrial consortium, is to ensure that the industry will comply with the Lunar standards, and so will be interoperable by design, both at IOC and FOC, the LCNS system. This could increase and maximize the business cases that could be captured by LCNS in the future. So the long-term objectives is to push forward, so you use the same technology, the same architecture in different contexts to maximize the deployment and expansion of the SSE architecture. So concerning the timeline roadmap is here depicted. Is very important to show that we are very close to the IOC launching date, because 2027 is very, very close. We will have a first batch of 2 satellites, a communication relay node and a navigation relay node, in 2 orbital plane in different with different orbital period to meet the ESA service requirement previously shown. And then after that, in phase 3, we will have a second batch. So we will have the announcement of the navigation constellation, or part of the constellation concerning navigation nodes, and then another communication relay node concerning the FOC capabilities. Concerning the architecture is here depicted. As I previously said, we have 2 communication relay node, one IOC, one FOC with different capabilities. Later on, we will see which are the services that will be delivered. And 4 navigation nodes in 6 different orbital plane. We will have a set of ground station networks equally spaced 120 degrees in longitude to maximize the Earth-link visibility. And then we will have an architecture based on commercial cloud providers. So this to speed up the deployment activities concerning the Moonlight infrastructure. Concerning the services that will be provided, here is depicted the list of services for communication, navigations, and other services, real-time services such as the Lunar Return Message or over-the-top services. The idea for communication services is that at IOC we will use pre-scheduled contacts. We will have DTN functionalities. And we will use all the waveforms concerning the single access link, so we don't have the spectrum. At FOC, we will have the user-initiated session establishment approach. We could have moon-to-moon communication, dynamic resource allocation, and we will use the spectrum waveforms. We also have the possibility to perform the direct within Earth services. This to maximize the availability of the communication services in this contact window in which there's no contact because the relay is not in visibility with the user assets. And then on the right side, we have the navigation. So at the beginning, we have only one navigation relay node, so we could only support this set of service. This is depicted in the upper right. Okay, I will go on. So concerning the key service requirements, the Moonlight infrastructure and Moonlight program targeted the commercial and institutional missions. The first launch will be at the end of 2027. The system is designed to be scalable and to be interoperable by design with LunarNet. So we really focus on the LunarNet version 5 specifications and on the regulations coming from the different regulation body or agencies. And then we target it to have open interfaces. So we would like to have to publish ICDs, at least for the Lunar Space segment to the Lunar User segment interfaces, to let manufacturer to build user terminals. Within the Moonlight programs, we also have companies that is dedicated to manufacture terminals for both common NAVE integrated terminals, because it's very important in our constellation. The constellation, as mentioned before, is targeted the South Pole coverage. The global coverage is in best effort with 200-kilometer altitude and support of mission phases all to the trajectories for a given assets in the lunar region. Concerning the performances for the communication, high rate links, we currently at IOC on the single access link, we target 60 megabit per second in return from the moon to the Earth and 20 megabit per second forward. For the low data rate, we have up to 1 megabit per second return and 200 kilobit per second forward. It is the use case that is the driving use case behind is the Argonaut missions that we mentioned at the beginning with the with Javier Ventura Reveset from ESA. Is secure by design, the system. So in each stack of the protocol, we targeting to introduce security features at Space Data Link, at the DTN link, and then concerning the performances of navigation, due to the short time, I will not enter into much details, but it is here depicted is in line with the expectations from the European Space Agency and from what is reported within the LunaNet specifications. For sure, these real-time performances will not rely only on navigation satellites, but so on the CIS, but on sensor fusion from different sensors. Concerning the open points for communication, so there's a major open points that is partially already discussed by my colleagues in SSTL, Rami. This is a slide to depict what, in my perspective and Telespazio perspective, should be really specified in the next version of the LunaNet specifications. So currently, it's still that the protocol will use hailing and the proximity 1 protocol for the link establishment mechanism for both S-band and K-band. And we know that for K-band, it's really difficult to think to reuse what is under work for the evolution of the S-band. Moreover, there's a lot of pending points that I remark here that, in my perspective, should be soon discussed and finalized to make sure that the LunaNet specification will be used for real from LCNS and in LCNS program. Because due to the tight schedule, we need to push forward the specification of the input. Otherwise, we could not be sure to be interoperable by design. This is a very important point. There's a lot of TBD and to be review points. It's clear that it's open now, the specification, so this heavily impact the interoperability. Concerning navigation aspects, this is my last slide, concerning the characteristics of the CIS-ICD, there's some other points concerning the IEQ channels of the AFS. So I here depicted some points that should be analyzed and discussed, and I hope that will be provided in the next version of the applicable document number 1 of LunaNet. And there's some uncertainties concerning the messages, the phase structure, and the overall implementation aspects concerning the LunaSAR return message. And also for these aspects concerning navigation services, there's a lot of TBD and and to be review points that heavily impact the design of the CNS infrastructure. Okay, so just to close with these key factors of LCNS is interoperable by design, or we hope to be interoperable by design when this information will be provided and make available. It's based on open interface, as I said before, is respects all the regulations, and our idea is that we would like to speed up the SSA deploy in the lunar region, and then I hope in different region of solar system. Okay, thank you so much.
Thank you very much. Is there a question, comment from the floor? I have one question regarding the IOC. You mentioned that one communication satellite and one navigation satellite. Could you provide us with the orbital information for these two satellites, if possible?
Orbital parameters you mentioned. Okay, so concerning the communication relay node, we will use 12-hour orbits, LFO orbits. Concerning the navigation node, we will be at 24-hour orbit. Different orbital period, different orbital plane.
Yeah, thank you very much. I saw on one of your slides you had build by design, and I was wondering how in that process you incorporate the actual CCSDS standards. Over.
Okay, so concerning the interoperability by design you mentioned. Okay, so in the proximity link, we targeting the usage of all the proximity waveforms concerning the single access link. Concerning the CCSDS specification and blue books, we envisage the usage of the data link layer of AOS, OSLP, and IOC and FOC with the feature of space data link security. And then an upper layer of the protocol stacks, we would like to go using link layer transmission protocol specification and encapsulation service specification and all the specification concerning the space link extension cross supports CSDS for frames service on the terrestrial link. So we are targeting to use all the things and materials that are available on the CCSDS to make sure that in each links, could be proximity link, could be terrestrial link or a trunk link, we could be interoperable because we use something that is already well defined and incorporated within the LunarNet specification that already say what you need to do in which interface.
Okay, thank you very much. Okay, the next presentation is from Andrea Domenico Morguglia from Thales Alenia Spazio, Italy. The title of the presentation is Multi-Purpose Habitation, MPH, Enabling Lunar Exploration and Lunar Services. Okay, please.
So good afternoon and good evening, everyone. My name is Andrea Murlia. I'm a telecommunication engineer for Thales Alenia Space, Italy. And today I'm really glad to be here in this beautiful location to present you MPH, Multi-Purpose Habitation, which is a project we are developing for the Italian Space Agency in close collaboration with NASA. So today, after an overview on the mission objective and the key points of the mission, we'll dive into two important subsystems for MPH, which are communication subsystem and PNT subsystem. But first, what is MPH? Well, MPH is a pressurized habitation module that will be positioned and operated on the moon on the lunar south pole. And its major objective is to safely host astronauts and support their activity both in EVA, IVA. But since astronauts are not going to be there all the time, well, we will also support scientific research and experiments by hosting payloads. And let's see an overview of the key points of the mission. So MPH will host astronauts. So it needs to support life and crew activities. And to do this, it needs to be independent and self-sufficient. It will be positioned on the lunar south pole. So it's critical to survive the lunar night. And this has huge impacts on several subsystems, such as the power subsystem that has other impacts, for example, on the mass target. Then we are thinking also to mobility system to relocate MPH to better accomplish its mission to other location. And here comes the mobility key point. And then, as I said before, astronauts are not always in MPH. So to support scientific research, we will host payloads, and MPH will provide these payloads with power, data, and volume allocation. So MPH will be one of the first habitation on the lunar surface, and it will have a huge amount of different capabilities. And one of these will be to provide services to other users, and especially PNT services and communication services in the frame of the LunarNet and Moonlight interoperability. So here we start with the communication scenarios. From the picture, we can see that MPH is at the center of really several links from the lunar surface to the lunar orbit, and it will communicate with different assets such as lunar relays in orbit, the gateway, and also direct to Earth. And all these links will enable its services, and it will enable users on the surface to exploit it to transfer their data, for example. And its services will be delivered to the different service volume depending on where the user is placed. So in the end, MPH, we can see it as a communication hub, since users may exploit MPH capabilities to transfer their data to Earth or even to other users on the lunar surface. And when we think of services delivered by MPH, we are in the communication, at least, we are thinking of real-time communication services and store and forward communication services based as on DTN. And those services are critical for all those users that may not have enough capabilities to transfer with enough performance their data to Earth or to other users. So MPH really could enable these users to have more performances. And in the end, for the communication services, also we are thinking also on implementing messaging service, but at this time, well, protocols are yet to be defined. Then the second subsystem that I want to introduce you today is the PNT subsystem. MPH will be a communication service provider and a PNT service provider. And for the PNT service provider, there are several use cases in which MPH could be really useful. For example, crew exploration in EVA, crew relocation, or the deployment of payloads and systems on the lunar surface, crew operation of mobility systems. And from the picture, we can see how MPH will interact with several other users and systems to run its PNT payload. When we think of PNT services for MPH, we are mainly concentrating on two important functionalities. The first one is that MPH will act as a pseudolight. It means that we'll broadcast the S-band navigation signal. And this is could be really useful for users on the surface, because at the first stages, there may not be a huge amount of satellites, navigation satellites around the moonlight, such as we have here on Earth. So having MPH acting as pseudolight could really be useful. And the second point is the generation of differential corrections, so differential LCNS. And also in this case, MPH could be an enabler for all those users that wants to enhance the PNT capabilities on the lunar surface. And in the last point, we have a communication subsystem, we have a PNT subsystem, so we have to exploit both capabilities. And exploiting them, we can think of providing additional services, such as a Lunasar, or just the dissemination of additional navigation parameters. So MPH can be seen in the end as really as a service provider, both for the communication point of view by providing essentially data relay services in different forms, and from the PNT point of view, acting as pseudolight, as differential correction generator, and as additional navigation parameter disseminator. And as you can see from summarizing what I presented to you today, well, if all the users that will exploit MPH capabilities will be interoperable, will be compliant with the LunarNet and Moonlight interoperability standards, well, MPH could really be an enabler for the lunar exploration for all those users. Thank you very much for listening. If you have any question, please.
Okay, thank you very much. A question?
Thank you. So will you add metadata to that pseudolight signal so that, you know, a passing satellite would know it's coming from the ground and it's coming from this location as opposed to some other location?
Well, there are we are at the early phase of the project, so all these details are yet to be, well, they are in this time they are traded off, let's say. So yes, we are thinking of techniques in order to let the user understand which kind of signal is receiving.
Because there might well be more than one pseudo light.
Yeah, we hope that.
Is there any question or comment from the floor?
Yeah, thank you for that nice presentation.
You're welcome.
So on the habitat itself, I see a lot of data moving around. And how do you see like a cloud capability there? Will it be there on the habitat or actually away from the habitat?
Well, the habitat will have its data handling system. We are foreseeing several mass memories with enough capacity to store all the data coming from the payloads and from the scientific research that the MPH will do, and also storing the data coming from the users that will exploit its services. At this time of the project, we don't really add cloud capabilities per se foreseen, but actually it's a really good point, and we may take in consideration that. Thank you.
Thank you.
Thank you very much. I would like to ask the expected year deployment of the MPS, if you have already some year timeline for the MPS deployment.
Yeah, we have a schedule, and the expected delivery date to the launch site will be at the end of this decade.
This decade.
This decade, yeah. So by 2030.
2030. Is there any question or comments? We still have a few minutes. If no, okay, then let's move on to the next presentation. Thank you very much.
Thank you.
Okay, the next presentation is from Farzana Kahatri from MIT Lincoln Lab. The title of the presentation is Lunar Optical Communications. Okay, please start.
Thanks a lot. So I just wanted to remind you guys about our work that we've been doing for many years on lunar optical communications, or basically laser comm systems. So this work kind of kicked off many years ago. 2013, we had the Lunar Laser Comm demonstration, which was a collaboration between many of the people in this room. Lincoln Laboratory, NASA, JPL, ESA, we were all involved in this. And this was the first demo that NASA did, which was a complete laser comm system. We showed 622 megabit per second downlink from the moon to the ground and a 20 megabit per second uplink. And we pretty much debunked all of the myths that laser comm is really difficult to do. I mean, we were able to point and track our narrow optical beams. We had error-free comm performance. We did it, when the sun was out, when the sun was, close to our field of view. We did it low in the atmosphere, or low in the close to the horizon, number of atmospheric conditions. We were able to downlink a gigabyte spacecraft memory buffer every day. This was 10 years ago. We did demonstrate applications of like HD video. We were able to show like 4 video streams going up and back. Because that was the way we had our video set up. We could do it all the time, every day. We also showed, as Vince pointed out, it was a demo of a delay tolerant network. And on top of that, we started dabbling in the PNT area by doing a time of flight measurement. And so this was 10 years ago, and very successful demo. This technology was transitioned back to NASA, and they built up something that's called the Laser Comm Relay demonstration, which I'm not really going to talk about because it's not lunar. But this actually did lead to a lot of work on standards. So again, a lot of the people in this room here have worked on the CCSDS standards for laser comm links. In particular, there's a standard called the high photon efficiency standard, which is used for deep space links. This standard, it specifies various modulation formats like PPM, coding and interleaving, and the wavelength at 1550. Also talks a little bit about beacon and polarization. This has been a very successful standard. In fact, it's in use today, I believe, on the JPL's DSOC system, which is an operational system today, which has been setting records like every day, and it's been really good. We also use the standard to to design the optical payload that's on the Artemis 2 spacecraft, and that is going to be launching in 2025. We had to modify this a little bit to put an Ethernet interface on it, but nevertheless, it's a great standard. And it's also being used at the ground stations on Table Mountain, White Sands. All these guys are using the standard. And in fact, industry built a lot of these modems, like CACI built it. And actually, the standard was sent out as part of a bid. So many folks actually saw the standard. And this is, it's out there, and people have built equipment for the standard already. So it's been great. And I think someone mentioned earlier today that going forward, they're going to be adding a coherent link to this. And that, it's perfect for our lunar trunk. So just a little bit about laser comm on the Orion vehicle. So this is the Orion Artemis 2 mission, which will be carrying the crew up to the moon. It's going to be launching, I guess, next year at this point. And on it is an optical comm payload. In fact, it's going to be like the main trunk back for real-time video. And so all the astronauts are going to be using this. If you see any video coming back from that mission, it'll presumably be on optical comm. But this is on it. It's going to be launching, payload's all done. And it's up to 260 megabit per second and 20 megabit per second for the uplink. And, like I said, real-time video, all using the CCSDS compliant signaling. Here's some pictures. This actually was on Facebook, and here's our payload right there. And I think just looking to the future, we've already demonstrated this works. There's nothing like new here. So I think designing this into a lunar relay, like a fat trunk, bringing back all of the data would be a great thing. And that's why I'm here at this conference. And I think people have been thinking about this. It's not like it's out of the blue. I've seen optical comm and laser comm in many of the presentations today. So that's great. So despite whatever is used for the proximity operations, I think, trunking things back by laser comm makes a lot of sense. So I just have a few takeaways. First of all, I think everyone has seen that report about the Deep Space Network being very, very congested. And that's another reason to consider laser comm. I think, trying to add more payloads and more users for DSN is just not going to work going forward. The other thing we've noticed, I think human missions, they need a lot of uplink bandwidth, and typically the RF systems don't provide that. Laser comm is a very good solution for that for human missions. And like I said, laser comm is here. It's ready to meet the challenge. We've already demonstrated it, like I showed you. We also have another payload on the ISS right now. It's called Illuma-T. I didn't bring a slide on that, but I will tell you that is currently operating, and it's doing an edge-to-edge all optical relay system. And that's going to be really neat. It's a 1.2 gigabit per second return link and a 155 megabit per second forward link. And that's kind of in there to sort of operationalize laser comm. And the idea is it make it like a precursor to a relay up at the moon. That's all I have. I thought it was a 5-minute talk.
Thank you very much. Any questions or comments from the floor?
What's the aperture size?
What's the aperture size for the space and the ground terminal?
So the space terminal is a 10 centimeter aperture, and the design we have actually is scalable. So it could scale up to 30 or scale down to 5 or 1, for example. The ground, there's a variety of different apertures. There's like a 1 meter, I think, at JPL, and 2 40 centimeters down at White Sands. So, a variety of different aperture sizes.
Gary Barnhart, ex-ISP Inc. Understand you've got first light to Illuma-T. What sort of latency numbers are you getting?
Latency numbers?
Yeah.
You mean in terms of getting the data back down?
Yeah.
So I don't know, you have to ask Dave Israel about that. That's not my forte. but I believe it's coming down pretty well. I do know we've invoked his DTN, and we're going to be doing some more networking demos in the next few weeks. So we've just done sort of preliminary networking demos for that. We haven't done the full edge to edge yet, truth be told.
Okay, are there any questions or comments? We still have a few minutes.
Yeah, thank you. You mentioned that the hardware was compatible to the CCSDS standard, and that the CCSDS standard was used as part, it was put out for the bid. Could you talk a little bit more about that in terms of how the hardware was made to be compatible to the standard? Did people respond to that in their proposals, or was it, or just maybe talk a little bit more about that? Thanks.
Okay. So when we went out for bid, actually the standard wasn't even finished yet. So we had a preliminary standard for the coding, interleaving, and modulation portion, which we sent out to the vendors, and you know, they were okay with it. We had to do a little modification because the Orion folks wanted an Ethernet app layer interface. So, you know, I think no one was shocked or upset or anything. You know, we sent this out. They all built it. There's, I think, a company out in California that helps. They've built a lot. I think for DSOC, maybe John Hampkins knows they built a bunch of stuff. So it's all out there, and people are building it for sure.
Okay, thank you.
Okay, thank you very much. Okay, no question or comments? Okay, then let's move on to the, thank you very much. Okay, the next presentation is from Peter Shams from JPL. The title of the presentation is Challenges for Secure Interoperability at the Moon. Okay, please.
Yep, it's me again. So I was up here this morning talking about CCSDS and all the things that we do with standards. And what I'm going to do this afternoon is not take an anti-CCSDS point of view, but just sort of step back from all the things that we're trying to do and try to point out in a broad sense some of the challenges that we've got. And please don't take anything that I say as insulting of anything anybody is doing. I think we're all sitting at a fascinating time. I'm a guy who grew up with 56 kilobit networking, and we've got gigabits coming back from the moon. That's magnificent. So you've seen a chart like this before. And this comes out of one of the IOAG Lunar architecture documents. And you know, I have this, and some of the things I say may be insulting to people in the room. I'm not trying to talk down to you. I'm hoping to get you to think about things from a slightly different perspective, because we look at these charts and they're very static, and they talk about, you know, links to here and links to there and data rates and things like that. And lot of stuff on the surface, stuff in orbit, stuff on Earth, stuff on the moon. It's really important to think about what are the sort of consequences of all of that. And so I want to step back from that and take a look at it. And one of the things that to remember, in particular in looking at IOAG Lunar is that we have to keep in mind, and we've heard a lot of this, this is going to be evolutionary deployment. It's not going to happen all at once. It's going to happen over time. It's going to happen incrementally. We've heard from a number of different agencies and different companies about the things that they're doing. So we've got all these different bits and pieces done by different organizations at different points of time, maybe picking up different standard sets at different points of time. There's some challenges that come out of that, because these things ultimately all have to work together. And that means we have to think ahead to where we want to get and aim at some interoperable target, and keep that in mind throughout all of this. And we've also got this challenge. We've got institutional providers, we've got commercial providers, we've got agencies, we've got these little companies, big companies. There's a lot of variability in there, and ultimately it all has to work together. Similarly, when we think about communications, I mean, the thing that I always keep in mind is when we're out in space, communications is the only thing we have that connects us. Those comm links, whether they're RF links or optical links. So what I'm saying is obvious. I know that. But keep it in mind as a perspective and thinking about things. This notion of interoperability and particularly security is important. And I'm going to provide a little motivation on security. Delay tolerant networking is what we're planning toward, but we know we're going to have IP in a lot of places. Are we going to have IP end to end? I don't think so. But if we're going to have IP, we have to think about how these islands of IP, call them islands of IP, are going to connect one to another. We're going to have these long haul links as well as local links. Some of them are going to be delayed direct to Earth, DTE. Some of them are going to be local and relayed. We have proximity links. We have LANs and WANs on the surface. And all of this stuff has to work together. And we've also, of course, got fixed assets and mobile assets. It's a pretty diverse kind of environment. So I want to explore some of the challenges a little bit. One of them is physics rules. You know, speed of light is an issue. Things in orbit is an issue. I want to talk about some of the features of this, and some of these features are actually really challenges. And ultimately, what I don't believe we have right now. I mean, I get to sit at a point in the system where I get to look at a lot of different documents describing a lot of different people's concepts. And what I'm not seeing is an integrated architecture that's really going to let it all play together and evolve. We've got a lot of different bits and pieces, and they don't necessarily all line up. So one way to look at that diagram is to think about, and here's where I may be insulting most of you here, everything is in motion. It's important not to look at this as a static thing, but as, oh, gee, you know, the Earth rotates. The moon goes around the Earth. The spacecraft go around the moon. The things move around on the surface. Everything is in motion. So these links, while you can look at them statically and you can think of them as fixed, they aren't. Nothing is fixed. Everything's in motion. And that has to do with, has to affect, you know, the communication services and how they work together. It's going to affect availability of the communications links. And there are all kinds of other availability challenges, like some of these things are providing services, we've heard that, but some of them are also providing science. And science may be their primary thing, and the amount of link that's available to support other people's communications may be a reduced asset, you know, a reduced resource. So how do you deal with that? We haven't had, I don't think there's been much of a talk yet about emergency communications and search and rescue kinds of things. That's another aspect of it. You know, we need to have interoperability, and we've got all these different entities. You know, are they going to all play together, and are they going to support some of these common services? And then there's the whole question of continuity. And how do we put networking on top of that? And then there's another aspect of this, and this is the thing that I described as a sort of DTN, delay tolerant fabric, because it has to be delay tolerant, right? Each of these elements is not going to be in continuous sight of every other element or continuously connected. Maybe it's on the backside of the moon. Maybe it's in, you know, it's something that's in orbit around the Earth. Maybe the asset you're using on the Earth is just rotated out of view, right? So everything's in motion. If we have these diverse protocols and these islands of IP, we're going to have to deal with how we do store and forward, because IP as out of the box doesn't give you store and forward capabilities. So if we have islands of IP, how do we connect them? What's the protocol look like? Is there some kind of, you know, protocol conversion gateway? Do we invent some new application layer protocols that handle that kind of thing? And then there's the whole question of application layer services, because even if we imagine using IP everywhere and imagine having continuous connectivity, most of these IP applications that we have assume really continuous connectivity and instantaneous connectivity, right? We're talking milliseconds, not multiple seconds. And if this architecture is going to work out at Mars as well, there is this notion of of Moon to Mars, we have to have an architecture that is Mars forward and in fact accommodates 10-minute one-way light times, not a couple of seconds. There's another aspect to this that we haven't really talked about in here, and that is that there are lots of different organizations and lots of different countries that are going to be present at the moon, already are going to be in the future. And I'm not even going to bother reading the list, but the obvious thing to start thinking about is how do we manage access controls? Are these resources that we put out there going to be available to everybody? Is it ubiquitous connectivity, as we more or less have in the internet terrestrially? Or are these resources sufficiently costly and sufficiently valuable that we don't want somebody else swamping them, whether it's intentionally or unintentionally? I mean, you kind of have to look at this and put your security hat on and say, oh, what if we're dealing with denial of service now? And there's some assets out there that are impacting our orbiting assets that are providing our communications. How do we manage all of that stuff? So I think access controls and policies and peering relationships among all these things, as well as all those interoperability points that several people have pointed to, are really essential. And we have to have some kind of governance mechanisms. So I think the solution for this, I'm a standards guy. I do think the solution for this is interoperable standards. I know you can't possibly read this. I mean, my eyes are old. I can't read it at all. Happily, I wrote it, so I remember a lot of it. The point I want to make, and you'll get to look at this and ponder over it when you get the slides, is the stuff in green is stuff that we have already. CCSDS and the IOAG actually have a lot in hand that is architectural and says, you know, these are the standards we have that'll make a certain bunch of stuff play together. We've got a number of other things that are in orange there that are in development. There's a set of standards you heard about earlier that are the orange standards. They're experimental. They're not fully cooked yet. They are experimental standards. On the other hand, they fill in some holes in the architecture that we're going to have to fill in that are related to all of these issues. And then there's a bunch of stuff that is listed in red that basically is things that we know we need to do. We need to have standards for managing identities and for managing routing and for managing the network. You've heard several people talk about that during the day. And I just want to draw your attention to it because it's stuff we are going to have to deal with. A lot of this stuff is identified in the standards plans. We don't have all the resources necessary to make it happen. And yet, if interoperability is going to take place, we must do it, right? And so, point I want to make here is we have some industry people in the room. We have people from different agencies here. We have an organization, CCSDS, that is working on a lot of this, IOAG as well, for that matter, and even in the IETF for some of the DTN stuff. And what I want to do is encourage everybody who's got an interest in it to come to the table and help make the rest of the standards that we need in here a reality. And I'm done.
Okay, thank you very much. Is there a short question? Okay, please. You, okay.
Okay, and I grabbed it first. Okay, so we talked about pseudo-lights a little while ago where something on the surface acts like it's a satellite. So I'm going to act as a pseudo speaker and answer questions raised by the speaker in reverse position there. So everything that Peter alleges here is correct. As Peter well knows, we're engaged in significant discussions. You heard about CCSDS's security working group. In the IOAG, we're also working on establishing a security working group. Peter and Daniel Fisher have volunteered to be co-chairs of that. We're working on terms of reference to establish that working group right now. It hasn't been stood up yet, but these are some of the problems that we know are challenges. We fully acknowledge that, and those will be things that the working group has to work and work them in concert with the CCSDS working group and other working groups, right? There are implications here for
internet security and, right, what does security mean on PNT protocols, right? If we look at GPS was built sort of like internet protocol back in the days when nobody attacked your positioning satellite. And so now we have serious problems with jamming and spoofing of GPS signals, and Europeans, having learned from that, have instituted an authentication capability for their open public regulated service on Galileo. So we're going to be looking at secure, and by secure, we mean end to end, right? It's got to go from control center on the Earth through system provider 1, provider 2, right? Ultimately to hops on the moon and to destination. Secure means end to end, not hop by hop. And that is a shift, right? Because traditionally we have primarily worried about encrypting the command uplink to spacecraft and not a lot else, right? Well, we bring most of the data back down unencrypted, and that will no longer be as safe as it used to be. So the biggest problem that we face here, as Peter referred to, is just a lack of resources, a lack of expertise within the space agency. So I want to second Peter's call for industry to help out on this. This is a deficiency in the IOAG LunaNet architecture. It's a deficiency in the LunaNet interoperability standard. It's a deficiency in the Artemis program's communication interoperability standard. It's a deficiency all the way around, right? So we know we need to build security in up front, and we're challenged to pull it off. So this is a call for help from anyone who's willing and able to help.
I just got one question, Jim. What was the question?
That was an answer to your question.
So, sorry, you mentioned islands of internet.
Yeah.
And I would actually suggest that there is a protocol called QUIC, which is internet over UDP. And that is used right now, and that has been tested actually all the way out to Mars distances. And so if you had a situation where you had a lunar base, for example, and you have a high bit rate optical communication back to Earth, it's more or less always on. QUIC would have a lot of advantages over DTN. You know, you wouldn't need all the bundle protocol overhead for that, because you would be basically just running the internet out to the moon. You couldn't do that with TCP, but you can do that with QUIC, and that's actually been demonstrated. I mean, not at the moon, but with those kind of delays. Delays are easy, you know. And so I think QUIC will have an important role here. Maybe not as important as DTN, but I definitely think it's going to have a role in this stuff, and I've been trying to promote that idea. That wasn't really a question either, but I'm sorry.
You know what? If what I said prompted people to think about things, that's a good thing. I'm aware of the QUIC work, by the way, and I think it's an interesting experiment and is worthy of further looking at. Oh, I know exactly who you're talking about. He's sitting in the back of the room. He's a good friend of mine. Okay, so but we need to look at all of this. And what we do know is that we need to look at ways of getting delay tolerance working. And nothing that we have right now does that completely. So there's work to be done. And I'm not shortchanging what you're saying. There may be multiple ones, but as a guy who lived through the time when we had UUCP and BitNet and this and that and the other thing, and when you wanted to email somebody, you had to tell the email how to go from point A to point B. That's kind of where we're at right now with all of this stuff. And what we need is really an internet that will work. So I'll stop.
Yeah, thank you very much.
Okay. The next presentation from Edward J. Villane from Johns Hopkins Applied Physics Laboratory. The title of the presentation is Security and Management of DTNs in a cislunar environment. Okay, please proceed.
Hi, I'm Med. With this presentation, I am a co-chair in the IETF working groups for DTN and time variant routing. So we do understand some of the protocols that we're talking about. I am a co-author of Bundle Protocol version 7 and co-author of BPSec, which are two of the protocols that we've also talked about. And I want to provide a couple of thoughts and status updates for where we are on security and network management, and perhaps protocols as well. The first thing I want to mention is, I don't think I've ever seen more pictures of the moon in a couple-hour period than I've seen today. But what most pictures of the moon don't show is the sense of scale. So I want to start talking today big. I want to get very small, and then by the end, I want to give you some free stuff. So if we start big, there's a picture on the bottom left here that's pulled out of a CIS Lunar Security National Technical Vision. There are many of those floating out there. That's actually two pictures. The first picture is the top picture, which is Earth to LEO to GEO. And we spend a lot of money to move networks to LEO so that we don't have them in GEO, because we can't get the kinds of experiences we want in GEO. A lot of money. Then there's another picture below that, which is harder to look at. And that shows the difference from LEO to GEO on the left, and then the difference from GEO to lunar. And if we talk about services and protocols, we can talk about protocols as data structures. We can talk about end-to-end connectivity, or we can talk about all of the services that make all of it work and configure and bootstrap. And we need to be very precise in how we chop this up when we say something's going to work and something isn't going to work. So there's more detail than we can get into in 7 minutes and 52 seconds. But here's a scaled picture of what we're trying to deal with. And the moon is pretty close. Something to think about. Here is a picture that doesn't show really the scale between Earth and the moon. But if we look at the kinds of things that we want to be able to do in general for lunar communications and cislunar communications, there are a couple of things that kind of stand out as being useful and helpful. One of them is store and forward data exchange. We do not assume that a path exists end to end. We might, through great expense, try and keep a link together all the time, or two links together all the time. Let's not make those assumptions the foundation of what we are building on. We do not control physics. We do not control celestial bodies. We do not control power and when our radios are on, always. So again, we don't assume that our endpoints remember things for us. That is a useful and something that I wish would be true, but it is not. The world is harder than that. We do not always have to retransmit from the source. We do not always have to start over again from scratch. We might have to store our data for milliseconds or many milliseconds. we might have to carry some data and metadata at the same time, which bundles do and other protocols do. From a security perspective, we know it's not just physical layer security because we're many hops in the physical layer. We might, if we're packaging and bundling different data together, we might want to secure those different parts of data differently, which is very interesting, even if you never have delay. If we are storing data and we do have security inside of our data layer, inside of our bundles, then we also get some security at rest, which maybe saves some processing. It's also things that some people are interested in. And if we want to manage our network, we have to have some autonomy in the network itself. As someone who did flight software for the New Horizons mission to Pluto, when you are 4 hours away, and the radio's on there because you're powered by an RTG, and something goes wrong, and you're 4 hours, 8 hours round trip, by the time you know something is wrong, your spacecraft is gone. That kind of rhymes. I like that. We need to be able to express network management semantics in a way that we can put on the spacecraft itself in a standardized way. Anyone who has written and built spacecraft understand that we do this, but do we do it in a standardized way? Do we do it in a network way? And then we're not going to get into routing right now. I will say, like many of us, I'm on mailing lists, many mailing lists. I'm on mailing lists that were very alive with traffic for people who are watching this live now. And on one of those mailing lists, someone put an email out that said, I will anonymize the names and the people, but company so-and-so started looking at everything that they would have to do. And they started with a traditional networking stack because they wanted to get something up and playing with it really quickly. And then they looked and said, oh gosh, how are we going to do store and forward? How are we going to do the time variant routing? Where are we going to put the autonomous management? And they said by the end, they would have created a custom one-off non-standard DTN. It's just cheaper to start with the decades of work that have come before and that is available. And we'll talk about that when we get into the free stuff later. So again, bundle and BPSec, I think, are useful things, and we should be looking at them as many folks are here. But this is where I want to get very small. Let's get down into the bits. When we say a bundle is a bundle of stuff. If we look at the picture on the bottom left, that whole big rectangle is data, is a single bundle, but it's got stuff in it. It's got primary blocks and extension blocks, and those extension blocks can have metadata and annotative data and link data and other kinds of data. And then there's this whole security protocol on the right with a really cool book about it, might I say, that comes back and says, how can we secure different parts of that separately so that as data goes through our system, we don't just reason about, I have to encrypt the entire thing. I can just encrypt for me the part that I want. I can encrypt my payload separately from how I encrypt a header that helps me get through the network. And I may never be able to decrypt the payload or go through the processing time to decrypt the entire payload. And I can just look at the parts that are interesting to me. It's a powerful capability, even at the moon. From a network management perspective, we asked ourselves the question, what is that intersection between spacecraft fault management systems and enterprise network management systems? As you might imagine, there's not a tremendous overlap here, but we think we found it. We said, you know, most spacecraft fault management systems, and many of us here who build spacecraft understand this, these are stimulus response systems. They must be deterministic. If your spacecraft has a problem, you need to understand what will it do? How will it demote? How is it going to progress? And when a spacecraft is acting as a networking node, that's no different. So there is new work coming up called delay tolerant network management architecture. It generalizes a typical flight software fault management and operational autonomy approach, but it expresses it using primitives and in a mechanism that are familiar for network management systems and able to then integrate and interoperate with terrestrial network management systems. It talks about managed devices and managing devices and not ground and flight systems. It implements a deterministic stimulus rule-based system, which we are very comfortable with in our flight software systems. I know we're all into AI and ML. No one's protecting $1 billion of asset just on AI and ML, right? We understand the baseline. You may build on top of it because you know you have a baseline. So it is enabling. We've talked about interoperability all day today. No one goes off into a cave and says, I'm going to go make my interoperable system. We have to show up. We have to show up here. We have to show up at the CCSDS. We have to show up at the IETF. The IETF is easy. It's remote. Anyone can join. They let me in. The DTN working group has a homepage that anyone can go to. You can watch all of the meetings on YouTube. You can join the mailing list. There are many, the IETF is also a big place, and there is a good communication and camaraderie between the IETF and the CCSDS. For example, Bundle Protocol version 7 is RFC 9171, published by the DTN working group out of the IETF, and then so profiled for space in the Blue Book that is coming out in a few months. As we build these things, let us not wait for things to be done and perfect before we decide to look at them once. So as we put out security, we at APL, we are putting out through NASA AMOS an open source BPSec library that anyone can use because that's open source. For the network management, we have supports, we have tools for agents that implement the standards as they are now, as they go through standardization. Through NASA Amos, we have management tools with graphical interfaces and Python interfaces and Python packages. Take them, play with them, break them, and tell us about it. Thank you.
Thank you very much. Thank you very much. Because of the time limitation, we cannot accept a question for your presentation. Maybe we can talk about it later. Okay, our last presentation is from John Hampkins from JPL. The title of the presentation is Technology Constellation for PNT at the Moon. Okay, please.
All right, thank you. Let's see if I can run the, okay, so this, so you may have heard of the Perseverance rover. It has nothing on you guys lasting for the whole afternoon, so I'm glad that you all stuck around and are able to attend my talk. So I'll make this brief. The main point I want to make is that we all know that there's this LunaNet interoperability specification document. There's a good reason why it's been inclusive and inviting a lot of inputs. At JPL, we didn't have a large role in its initial development, but we were sitting around and saying, look, we've got experts in atomic clocks, both on the ground and in space. We have experts on radio design and GNSS systems and PNT, particularly in the deep space area. And people argue, is the moon deep space or is it near Earth and so on. But anyway, so what we thought we would do is put together the expertise that we had and really take a look at technology gaps. And so I think we've heard some speakers here say, look, we have all the technology we need and we're ready to go. We're at high TRL. And then others have said, hold on, there's a lot of work yet to go. And so we took a technical look deep down in some specific areas and tried to come to some conclusions about where there are some gaps and where investment in technologies might actually save you money in the long run by doing some development of efficiencies that cost a little bit now and save you over the long run, both at the moon and eventually on the Moon to Mars program. And so a lot of our ideas are captured in a December white paper, which some of you may have seen. It's on the IOAG website, but it's also being published to, and this whole presentation will be available on the, well, I'm not sure where it's being published, but it's okay, on the CCSDS website. But in any case, it's easy enough to remember the Interplanetary Network Progress Reports, IPNPR, .jpl.nasa.gov, and on the 15th of May, this description will be coming out. And so there were a lot of conclusions that this is a pretty detailed report, but there's a few things that I'll just highlight in a few minutes. One of which that we called for essentially exactly what OSTP was echoing, or not that they were following us, but I think great minds think alike in terms of the need for an LTC that's something different than UTC for running our clocks at the moon. So one of the areas in which we think there is some need for technology development is in atomic clocks. Of course, there are atomic clocks that are already on our GPS satellites. Those are generally rubidium clocks or cesium clocks. They have 10 to the minus 11, maybe 10 to the minus 12. But even those clocks, say in GPS, we refresh them multiple times a day from Earth. Maybe that's not generally appreciated. Now, if you have to do that same thing at the moon, and now you have to use maybe DSN assets with large antennas or some other assets with large antennas, that starts to get burdensome when what you really want to use your antennas for is the comm part. And so there is some advantage in having a higher performing clock that you don't need to correct quite as often for the application that you have in mind. And so this is a scatter plot. It has a lot of different attributes to it. So squares are for the ground, circles are for space, larger circles are larger volumes, and smaller circles are smaller volumes, and so on. But it just gives you a smattering of a sense of what kinds of materials are. Of course, the ground clocks are capable of maybe a much higher stability. You can see on the lower areas of this plot, the ones in space are further to the right because we don't touch them after we launch them. But we do want to operate in this that little pink rectangle there, or maybe even lower for our science applications where we may want some really accurate clocks. And so each one of these dots on here is explained in some more detail in the report, and what it would be useful for, and what we could gain by some additional capability in this area. Another area is in our radios and transponders. And no matter what we deploy, so this is just a representative example of kind of the radios that we have at JPL, and some of the, like the Iris radio does, you can put on a CubeSat. It's very small, very light, not quite as capable. Then we have what we call the universal space transponder, and that's a much heavier, more capable multi-band radio. But no matter what we do, we're going to have to incorporate whatever LNSS or GPS-like capability in our radio. We're going to have the bands that we are going to need for all the services that we're going to have at the moon. And none of the radios that we have do exactly what we need yet, so they will all have to be adapted and made to be interoperable as that interoperability standard comes to fruition. So that's another area in which we can't just fly what we have now, because that's not going to be something that's interoperable across companies or across space agencies. And then also ranging and other PNT-like technologies. Right now, for example, CCSDS has an emerging optical ranging standard. It allows you to determine the range directly from a telemetry signal. You can have an RF uplink and an optical downlink even, things like that. There's also, of course, existing PN ranging or telemetry ranging signals, and the LNIS spec allows for both of these types of signals. But like optical ranging may have it's going to have the highest capability, most likely sub-millimeter, not counting the calibration errors that you would get on the ground in spacecraft, but just kind of physically, the fundamental physics of the equation is such that you have power such that you could get super accurate computations of range, and so this will be another thing that will have to be worked out in detail. And so I'll say in summary then that I encourage you all to go out to look at this white paper or article, this IPN progress report. And the other thing which I didn't really mention, but which the paper gets into quite a bit, is that we're all concentrating on the moon now, but what is going to happen after that is Mars. And a lot of what we are envisioning for having a navigation satellite system around the moon, we say, well, just move it to Mars. And a lot of that is true. A lot of that will carry over. Some things won't carry over, though, because one of the main technologies that is envisioned for the moon is using a weak GPS signal, as we've heard. And even if you're, I think the previous speaker showed a to scale representation of Earth and Moon. And if you think about it, when you're at the moon, you're looking back at Earth, the angle that is separated by the GPS satellites might be about 6 degrees, I think it is, which is really tough geometry, but you can do it and you can still resolve where you are at the moon. But when you're at Mars, that is going to be 5 millidegrees, and so that doesn't work out. It doesn't work out the angular resolution, and then of course you're 1,000 times farther as well, and so the link budget doesn't work out either. And so you do need a different fundamental architecture for getting your orbit determination, or your situational awareness of where you are, and how to then provide the services, the timing services to your users. And so we should be thinking about now what we want to deploy at the moon that will be a stepping stone to Mars, so that we don't have to start from scratch when we do the moon to Mars aspect of it. So, okay, with that, thank you.
Okay, so this is the end of the panel 3, and let's thank again for all of the speakers in this panel, and thank you very much for your participation. Thank you very much.
We're doing relatively well on time. I want to see if there are questions for John or Ed. Real quick questions. Is a microphone, please?
Yeah, thank you, John. I listened to your talk, and I was the one saying that we believe in ESA that we have the basic technologies for the lunar navigation. And when I listen to what you tell me, I confirm we have those technologies. It is more difficult to go to Mars, but let me ask one by one. So when you say we have clocks which are available, and indeed we have rubidium clocks, and mini-RAV, this technology is fully super proven. Putting that in a lunar satellite is not what you claim, but now you need to update. Yeah, I know that. And you need maybe a deep space. We don't need a deep space. We need a 90-centimeter antennas, and we have an update rate of about 2 hours, and that's sufficient. One important thing is that the signal in space error, we are asking for our initial, it is of the order of 10-15 meters, while on GPS and Galileo, we are talking about 0.7 meters. So it is much less demanding. So we can let the clock also, I'm talking for the initial services. The receiver technology, it is a different frequency. It is essentially the same receivers. We are using a protocol, I think in space, which is very similar. We are already having receivers under development. We need to do those. But technology-wise, there's nothing especially complicated. The orbit determination time synchronization for the moon distances, the deep space technology we have, again, for relaxed orbit determination we are not asking centimeter accuracy, we are talking 10 meters. Again, we have the technology, and our simulations show, indeed, we can meet those well. So I keep telling that today, at least for the systems we are conceiving Genesis like, we have the technologies.
Okay, thank you. No, thank you. I mean, it's appreciated. I mean, I think I'm not disputing what you're saying. I think it depends on the application that you have in mind. And yeah, anyway, I don't think we disagree maybe as much as we think, but I encourage you to look at the paper and see if there's anything we disagree on, we can discuss more.
Yeah, Gary Bard with XISP Inc. again. If you've got the clocks that effectively can be reset, and you've got a datum, and you can calculate the drift, can't you create a situation where we, instead of dealing with a weak signal, we can have a known set of signals?
You can always use, so drift, we would only be talking about the residual drift, I think, of things that you can't predict. I'm not sure I understand the question fully.
So the question comes in is that we would, right now we've gone a 2+ satellite fix on GPS from a lunar orbit. Arguably, there is some above constellation orbit where you can get an assured 4+ satellite fix, which is about as good as you can get. You can do the same thing with Galileo and several other systems that happen to be out there. If you have something there, it could be effectively a datum. It's a navigation marker if it's passive. It's a beacon if it's active. If there's more than one of them, you can triangulate. And then the drift, what I was speaking of, was the drift in time. Okay, the things we've got in our pockets reset almost constantly whenever there's a new transaction. Okay, if we drive the overhead penalty for that down low enough, aren't the pieces there that we could orchestrate to give us a much broader capability?
You mean with weak signal GPS?
Yeah.
Yeah, I mean, yes, you can look at the aspect. There will be, because they're all in the same part of the sky, you're going to get a worse GDOP and things like that. So you live within that limitation, but as long as that meets the requirements that you have, then you might be okay. not all the requirements have been set, and, you know, I think it really takes a longer discussion to answer the question. Yeah, thank you.
Great, thanks. Okay. I'd like to see if there are any quick questions. If we can. For Ed, because I thought it was a great talk, but no, yes, for Ed. There's a half question, and there's hesitation. Okay, as she gets the microphone, can I ask Klaus-Jürgen, Taya, just come up to the table. Jim Shear, we'll do the final segment with the panel chairs and our co-host, and then we'll hear from Dr. Diane Howard if she has any instructions or last minute thoughts. So what was, Ed, you want to come up here to take your question?
Yeah, thank you very much. Just a quick question. I heard a lot about things like risk and risk reduction in your presentation. And I think of the NIST cybersecurity framework, which is all about reducing risk. And I didn't hear the cybersecurity framework mentioned. So I was just wondering what your thoughts were on that quickly.
Oh, I'm a big fan of the cybersecurity framework. I do think we have to reason through the risks. I've never seen anyone reason through even one risk in 10 minutes. But one of the things is in the BPSec standard RFC 9172, there's an initial inkling of security considerations. And those, and then in some of the other literature that's come up around it, there is the building of, if we add security at rest into the sense of security in the network, those are things that have been typically separated, right? You pull something out of a tunnel, you resecure it down for storage, you pull it out, you re-encrypt it in a tunnel. What happens when you allow that additional kind of modality? So because we're doing new things, because we need to do new things, there might be other risks or combinations of things that we would consider unrisky independently, but are risky when we try and put them together. So we have to do that analysis. I completely agree. Yeah.
Thank you. Okay, you're almost free. Thank you, everybody, for coming here. We really appreciate it. I thought it was a great, productive day, and hopefully this is just the beginning. Perhaps we can do this again, but it at least kicked off some very interesting conversations. So I'd like each of us to kind of take 30 seconds, give or take, here at the table to kind of give your impression of what's going on. And then we'll see if there are any general questions from the audience. And we'll try to get out of here before 3 o'clock. But before we do all that, I want to see if Dr. Diane Howard has any closing thoughts or instructions on how to get to the steps, or what do we do? Come on.
First floor, we'll go out the Navy steps and we'll have a we'll have a wonderful photo opportunity. Again, secure your badges. I also want to thank you all for being so patient and dealing with the constraints that come with being in a very secure location. But it's been wonderful having you. And my biggest and most wonderful takeaway as a lawyer is to hear in a very technical forum, to hear that terms matter, because we say that all the time. The definitions are so key. So we have common ground. So thank you so much. I actually followed about 50% of what you said, and thank you for that.
Okay, before we start losing people, again, I want to thank Dr. Diane Howard for hosting us, and Dr. Diane Poster for co-hosting us, and everybody who helped out. Angela, thank you very much, and please give a big hand for Amber for weeks of hard work. And for the CCSDS organization overall, especially the CESG headed by Dr. Klaus-Jürgen Scholz, who can give us your impression of today.
Yeah, thank you very much of being hosted here. I would like to maybe give a bit of a summary what I learned here, or what I learned actually also last week. What is of fundamental importance is the combination of the communication and the navigation solution around the moon. And unfortunately, we do not have all the technical standards to make this really happen. We cannot really fully build the system now. We still need to work on the standards. And I'm inviting the members from the LunarNet community to think about to eventually standardize the GNSS-like signal within the CCSDS method, let's say standardization methodology, because I think that would really help to fully create also an international recognized standard beyond the 3 space agencies that are cooperating right now. I think we need to keep that in mind, and this is what I learned from this session.
Again, thank you very much for CCSDS for organizing this wonderful forum. And as I mentioned in my presentation, the interoperability and compatibility is the key issue for the future success for international lunar PNT systems. So JAXA and Japan are very happy to work with NASA ISRO under the framework of LunarNet, and we would like to continue this effort to actually make our system happen around the moon. And yes, and again, thank you very much for this wonderful workshop. And yes, I'm happy to work with NASA ISRO, and thank you very much.
Thank you.
So I will start out with a similar thanks to all those of you who made it to the room today to attend the whole session, and especially to those of you who either weren't able to make it or weren't able to get into the room and are online participating vicariously. Thank you for participating, and we look forward to working with you in the future as we have in the past. Two things that I want to pick up on that have already been slightly mentioned. Klaus Jürgen said that we need to continue working on standards, but there's a more fundamental problem. Before we get to standards, we usually have to define requirements, concepts of operation. What are our objectives? Where are we going? Why are we doing it? What are we trying to obtain from our multinational investment in the moon and beyond? And those drive the definition of the capabilities, which drive the definition of the PNT capabilities that we need to support the mission. So while we're still sorting out what's the Artemis campaign, what are the international partners contributing to all of that, there's still a lot of uncertainty that swirls above the level at which the LunarNet or the COM and PNT infrastructure can be decided. So we're going to have to put up with a certain degree of uncertainty while a lot of that gets sorted out before we get down to figuring out what the COM and PNT requirements are, and then we get to the standards. So there's still a bit of pipeline here that we have to work on in terms of the overall, not just system engineering, but in terms of the agency objectives for the various partner agencies in this. And this is going to unfold over the next 10, 20 years. That we can spend the rest of our careers on this. The other aspect of this is I particularly appreciated the way that the forum here was pulled together, that had the height and the breadth and the depth. We talked about communications, we talked about PNT, we talked about networking, we talked about technical aspects, we talked about governance, we talked about the legal framework. These are all relevant parts of this, and we can't do it without addressing all of them. So there's a really big framework into which our focus here fits, and we'll have to be aware of and participate in the definition of that, not just focus on standards, although right the orientation here is heavily standards based, but there's a bigger world out there that's more complicated even than we've addressed here. But I think you heard pretty much the state of affairs, right? We're in terms of our definition right now, we've got communications pretty well nailed, right? There's existing decades of communications and standards behind that. We're not so well defined in terms of networking layer capabilities or the architecture to do that, but we have stated publicly full intent to adopt that, implement that, and it's in the works. In PNT, we're in the process of defining that, but it's much more immature. It's much less based on existing standards. There is a lot more technical depth to be plumbed on that before we get to the requirements, the architecture, the standards that fall out of that. That's going to take a longer time to formulate and produce results. So expect, and then we talked about security briefly, and that's another missing hole, right? So there's aspects of this that are mature, immature, and barely crawling at this point, not up to walking yet. So there's a wide disparity across the domain that we're talking about. And the last thing I'd mention is somebody referred to NASA's LunaNet. I'm trying to stomp that out. It's our global, LunaNet for humanity. But we just coined the name.
Thank you, Jim. Does anybody have any question for anybody up here on the panel, or doesn't have to be a question if it's an interesting comment, and if it's for one of the previous speakers, we can give them a mic. Anybody? Javier. Okay.
All right, so who's going to be the first LunaNet service provider?
Next.
We volunteer, but we volunteer. No, thanks very much. First of all, I wanted to thank really for the excellent organization and my role at ESA as Moonlight Navigation Manager. And I think for me, some thinking is number one is we are all convinced we are doing the right thing in the right time. Communication, navigation, the moon. There is really a clear vision that this has to be done. There is a clear, I think, synergy on the room here that this has to be done through institutional and commercial providers in the right combination, as we are trying, and this is the way to go. I think another conclusion is that the cooperation between space agencies is very good today, and this has to keep going in this direction. We see that these cases of the moon, it is not only so important for the moon, it is setting up the standard for Mars and for the solar system. So we need to be careful not to be lunar centric and to really think always on the extrapolation and the scalability from all the moments in the standards. And for me, another message, more as an engineer, and we are implementing our system with industry. And by the way, thanks for our industry being here as well. It is it has been working in standards many years, is also the approach of being very pragmatic as far as we can. No? For example, Jim, when you say GNSS standards are super defined on the Earth, for example. And what we are doing in the LunaNet, and Cheryl is helping a lot on that, is actually making a standard, at least for the PNT, which is based on something very solid, which is used every day in billions of receivers and extrapolating that to the moon. So we are convinced, for example, that letting us working in this direction, it is very pragmatic. It is well understood by the ex-specialists on that. And we are in favor, at least on my case, and this has to become GNSS standards, but at least I really would like that we are following this very pragmatic, based on existing things, more trying to reinvent a lot. And when I claim all the time that the technologies are there, again, are based on technologies which are existing, very well proven, extremely efficient. So there is nothing that prevents to apply the same standards on the moon. And that's a message I wanted to convey. Thank you.
Thank you. Thank you very much. Anybody else? Yes.
Also, thank you very much from my side. Maybe just to close with what we began with, the first presentation was solar system internet, for the keynote that was given. And to me, the takeaway from this is solar system internet is the bigger context than the lunar interoperability. And in one of the slides, it was shown the IP islands. Let's say this is even beyond the moon, and around of it is an island within the same internet. So hopefully the context that we are discussing is a network that will be in LEO, GEO, around the moon, in Mars, and changing the way that we are doing space operations in future under the umbrella of the solar system internet. At ESA side, we are taking this serious as a vision for the next preparations of our programs. And I believe it is a common vision that we are sharing among the different agencies.
Excellent. Thank you. Eric, yeah. Behind you, Eric, there's a mic.
Yeah, I have a big question as to what comes next, and I'm not going to try to tackle that. But I would say from the standards point of view, I think one thing that was very interesting for me, I saw a lot of good industry presentations. I would like if there was some way that industry representatives could actually contact CCSDS, provide information. I saw talk about modifying Prox 1, et cetera, those kind of things. I'd like to hear more about that. As you implement things, what do you find about these standards that does not work, that needs changing, those kind of things. So I'd just like to encourage that kind of interaction.
Indeed, yeah.
So on that, there are two groups in the US at least. There's LSIC and then there's a new Logic, and those are both about standards really. And so I don't know if the CCSDS is talking to them, but they should be. But I mean, if I was saying, oh my God, this standard is broken, I would go to either LSIC or Logic first and try and push it through that way. Well,
Yes.
I might contact these guys, but you know what I mean.
Yeah. Thank you, thank you. Okay, it looks like we're very close to adjourning. Barring any other comments from anybody here, anybody on the floor? Okay, thank you very much. We're adjourned.
Excuse me, you all need to take everything with you because we will not be coming back to the room. There is another event scheduled for after us, so we need to take everything with us when we go. Thank you. No, you did a good job. You were on top of it. All I did was walk around and find jumping around. No, I like when you gave them the glares with the time, like, where's the hook? Right, like yeah. Sammy just kind of couldn't understand a word he said. Yeah, I'm sure. Good job. Yeah, get that. Thanks.